Let us consider an Atwood machine as shown in the figure. We have a pulley which is fixed at point O. A string of length L is attached to a mesh, say M1. So we have the following system in which we have the system as shown in the figure. Here I have a frictionless pulley which is attached to a point O. I have this string whose length is L. The distance from O to M, let the distance from O to M be x, and the distance from O to M2 will be L minus x, as the total length of the string is L. So we have this system. Let us just assume that M2 is slightly greater than M1. So the M1 is pulling the M1 downward. We are going to use the Lagrangian equation to find the acceleration of this system, and as we know that the Lagrangian equation is d by dt of partial qj dot of L minus partial L by partial qj is equal to 0. This is our equation number 1. If we look at our system, we have just only one degree of freedom, and that is x, which is varying with time. So our equation will become, in term of x, d by dt of partial by partial x dot L minus partial L by partial x is equal to 0, and this is equation number 2. We know that L is equal to T minus V. So we need T and V. T is the kinetic energy of mass M1 T1 and kinetic energy of mass M2 T2. So the total T is half M1 x dot square plus half M2 x dot square. So we have the kinetic energy which depends on the velocity, and the velocity of the system is x dot square is equal to m1 x dot square plus m2 x dot square, that is half m1 plus m2 times x dot square. So this is our equation number 3. Similarly, potential energy is sum of V1, that is potential energy of mass 1 and potential energy of mass 2. So net potential energy is minus m1 gx plus minus m2 g L minus x. And L becomes half m1 plus m2 times x dot square minus minus plus m1 gx minus minus plus m2 g L minus x, and this is our equation number. Let's call this equation number 4 and this as equation number 5. Substituting, so we need to differentiate equation number 5 with respect to x dot and then with respect to x, and then substitute the result in equation number 2. We get, by differentiating with respect to x dot, partial L by partial x dot is equal to partial by partial x dot of 1 by 2 m1 plus m2 times x dot square plus m1 gx plus m2 g L minus x. So the only term that involves x dot is the first term, that is the kinetic energy term, that is half m1 plus half m2 x dot square. The derivative with respect to x dot of the rest of the term shall become 0. So we will have m1 plus m2 times x dot partial L by partial x dot. Let us call this as our equation number 6. Similarly, partial L by partial x is equal to partial by partial x of equation number 4, equation number 5, that is half m1 plus m2 times x dot square plus m1 gx plus m2 gl minus x. Right? So these two terms involve x and they could be differentiated with respect to x, while the derivative of this term with respect to x will become 0. So we will have partial L by partial x is equal to m1g minus m2g, as m2gl is a constant whose derivative will become 0, and we are left with m2gx whose derivative is m2g, and this will become m1 minus m2 times g. Let us call this equation number 7. So 2 implies that d by dt of m1 plus m2 times x dot minus m1 minus m2 times g is equal to 0. This will become m1 plus m2 times x double dot, that is acceleration, is equal to m1 minus m2 times g, or x double dot is equal to m1 minus m2 divided by m1 plus m2 times g. That is, the acceleration produced in our Atwood machine will become equal to m1 minus m2 divided by m1 plus m2. So that was it. Thank you so much.